Welcome to section 5.3, Differential Equations, Growth and Decay. Our goal today is to solve differential equations that involve growth and decay. So our first theorem, exponential growth law, if dq dt is rq and q0 is q sub naught, that's our initial, then q is q sub naught times e to the rt. Q sub naught being the amount of Q at time 0, our initial value, like I said. R being our growth rate, we always express it as a decimal. T is time, and Q is going to be the result, the quantity at whatever time t we're choosing. Here is a table representing our exponential growth. So unlimited growth, we have dy dt equals ky, k and t being positive, y of 0 is some constant c. Then our solution is y equals c e to the kt. This fits our growth theorem where we have our initial times e to the kt. Exponential decay is similar, except we have a negative k. And then our limited growth, this is something that's not going to just keep growing continuously. This is something where we're going to have a limit. This is represented dy dt equals k times m minus y, making our solution y equals m times that 1 minus e to the negative kt. And then we have something called logistic growth. And logistic growth is where we have usually a representation of populations because they become limited on their resources. If we look at a population of bunnies, they can only grow to however much grass is in the area for them to eat. So the logistic growth model represents different populations and the restrictions that are on those populations based on other aspects of what will keep them alive. Okay, so let's use some of these models and our talk about growth and decay. In problems 1 through 4, find the general or particular solution as indicated for each differential equation. So number 1, we have dy dx equals 14x to the negative 8. If we multiply both sides by dx here, then we'll have dy equals 14x to the negative 8 dx. And at this point, we can integrate, and we'll have y equals this integral, 14x to the negative 8 dx. If we take the integral, we'll get 14x to the negative 7 over that negative 7 plus c. And we can simplify. 14 over negative 7 is negative 2x to the negative 7 plus c. And that's our solution. That's what we're looking for. Okay, let's look at another. dy dx equals 18x to the 5th, e to the 3x to the 6th. So now we have a little bit more of a complication. We have an exponent in our exponent. We also have y of 0, this being 7. So we have our initial value now. What we're going to do here is we'll use u substitution. So I'm going to let u equal that 3x to the 6th. That way this becomes a much simpler e to the u. Then we've got du is going to be the derivative, so we have 18x to the 5th dx. And luckily we see that here. So we'll start by rewriting. So if I multiply everything by dx, we have dy equals 18x to the 5th e to the 3x to the 6th dx, and then make our u substitution. So we are going to have the integral of e to the u du, and taking the integral of e to the u is just e to the u plus c. And so our solution is e to the 3x to the 6th plus c. So y of 0 equals 7, and y of 0 is e to the 3 times 0 to the 6th plus c. So we'll have 7 equals e to the 0 plus c. So 7 equals 1 plus c, then c equals 6. So this gives us what we call a particular solution because we know what c is now. E to the 3x to the 6th plus our c value of 6. Number 3, dy dx equals negative 8y. This is one of our exponential decay functions from the table that we started with. And using our table, we know that our solution to these types looks like y equals c e to the negative 8x. And as you get more used to recognizing these problems, you'll be able to refer to their solutions without the table. Number 4, dx dt equals 7x, and we have an initial value x of 0 equals 6. So this one is our unlimited growth. And so, using our table, we know our solution will look like x equals c e to the 7t. But we have that initial value, x of 0 equals 6. C e to the 7 times 0, which will give us 6 equals c e to the 0, 6 equals c times 1. So our particular solution will be x equals c, which is 6, e to the 7t. Okay, find the amount a in the account after t years if dA dt equals 0.02a and a of 0 equals 8,000. So this one is our unlimited growth. And we're also given our initial amount. So we'll have a equals c e to the 0.02t. And we can do the same. A of 0 equals 8,000, which equals CE to the 0.02 times 0. This is going to lead us to the same result where it equals C. So our particular solution in this case, A equals 8,000 E to the 0.02t. Okay, a single injection of a drug is administered to a patient. The amount Q in the body decreases at a rate proportional to the amount present. For a particular drug, the rate is 8% per hour. Thus, dq dt is negative 0.08 q, and q of 0 is q sub naught, where t is time in hours. If the initial injection is 10 milliliters, so q of 0 is 10, find q equals q of t, satisfying both conditions. Let's start with that one. So we have an exponential decay based on the amount of the drug decreasing. So we'll start with our equation q of t equals, we're starting with 10 mils E, and then we have negative RT, so it's decreasing at 8% per hour. As a decimal, we have 0.08, and T is just T. If how many milliliters to 2 decimal places are in the body after 6 hours? So now let's use our equation. We'll plug in 6. We're wanting q of 6. So we're looking at 10 e to the negative 0.08 times 6. And this will give us 10 e to the negative 0.48. So we have approximately 6.19. So we'll say after 6 hours, approximately, or about 6.19 milliliters will remain in the body. How many hours to 2 decimal places will it take for half the drug to be left in the body? So the initial injection is 10 milliliters. That means half of it will be 5. So we want to know, when will there be 5 left? When will q of t equal 5? And q of t being 10 e to the negative 0.08 t. So now we're solving for that t value. First, let's divide by 10. So we have 0.5 equals e to the negative 0.08 t. If we take the natural log of both sides, then that will take care of our e. So we have the natural log of 0.5 equals negative 0.08 t, and we'll divide by that negative 0.08. So t is going to be approximately 8.66. So we can say it will take about 8.66 hours for the amount of the drug to be half of the initial amount. A company is trying to expose a new product to as many people as possible through radio ads. Suppose that the rate of exposure to new people is proportional to the number of those who have not heard of the product out of L possible listeners. No one is aware of the product at the start of the campaign, and after 15 days, 50% of L are aware of the product. Mathematically, dNdt equals k times L minus n, and n of 0 equals 0. N of 15 equals 0.5 L. Solve the differential equation. So we have limited growth here. Because once someone knows about it, then that's one less person that the ad will be new to. So we can only grow by however many listeners have not heard about it yet. Once everybody's heard it, we've reached everyone and there's no one else new for it to hear. So our equation is going to be n of t equals L, all the listeners, 1 minus e to the negative kt. So we want to find what k is to finish our equation here. One thing that we know is that n of 15 equals 0.5 L. And so we'll take our equation and plug in 15. And now we can solve for, I put the wrong letter. 15 is the T, we're wanting the K. So let's start by dividing the L. So we'll have 0.5 equals 1 minus e to the negative 15k. And then we can subtract 1. So we'll have negative 0.5 equals negative e to the negative 15k. And since both sides are negative, we can divide by a negative and make them both positive. Now we can take the natural log. Natural log and e take care of each other. So we have natural log of 0.5 equals negative 15k. We'll divide by that negative 15. So k is going to give us 0.046. So our solution, n of t equals L times 1 minus e to the negative 0.046 t. What percent of the listeners will have been exposed after 7 days of the campaign? After 7 days, that means t is 7. So we are going to look for n of 7. We'll have L times 1 minus e to the negative 0.046 times 7. This will give us L times 1 minus 0.72468, which will give us L times 0.275302, which we're approximating here 0.275 L. So after 7 days, about 27.5% of the listeners will have been exposed to the product. And part C, how many days will it take to expose 75% of the listeners? So now we want to know what T is, N of T. We don't know what T is, but we want it to be 75% of the listeners. So if N of T equals 0.75 L, that's what we'll start with. And what is N of T? Well, N of T was L times 1 minus e to the negative 0.046 T. And now we'll solve for T. So we'll divide by L. We have 0.75 equals 1 minus e to the negative 0.046 T. And we'll subtract 1. Negative 0.25 equals negative e to the negative 0.046 T. And we can multiply by a negative 1. We'll take the natural log. So we have natural log of 0.25 equals negative 0.046 times t. Divide by negative 0.046. And we have t is about 30.1. So it will take about 30 days to expose 75% of the listeners to the new product.